Hello. In this video we'll be talking about search problems and representing search problems as graphs. So what is AI about, right? The goal in AI is to get computers to solve problems for us. And that's going to basically break into two stages. The first stage is to find some representation of the problem, find a way to encode the problem. And then the second stage is to develop and write algorithms that will actually solve the problems that we want to solve. So a theme of this class is going to be that it turns out that a lot of the work turns out to be in that first stage, just finding the right encoding for the problem. And often the right encoding, the right formulation of a problem is going to be driven by the properties of the problem. So we'll look at a number of different ways of encoding problems throughout the course. And in each case, it'll be driven by a different kind of problem that we want to solve. So for today, we're interested in search problems, deterministic search problems. So let's take a look at the textbook and see what it has to say about that. Okay, here's our textbook. We'll be skipping down to chapter 3. We won't look at this, but you should read it. Great stuff. Let's take a look here at section 3.2. And here's the bullet list that describes the properties of the problems we're interested in right now. So perfect knowledge, observable environments. So the agent knows everything that there is to know about his world. Actions with known deterministic effects. So we know exactly what actions are available to us. We know exactly what the outcomes of those actions are going to be. Some states are goal states. So there's some particular goal we're trying to reach, often just one goal state. And what we want is a solution, a sequence of actions that gets us from wherever we are to our goal state. So here's the first example from the textbook of a problem like this. We have an overhead view of some office environment. And the states are labeled O105, O103, etc. And the idea is we have some sort of robot maybe who's trying to deliver packages within this environment. And he has deterministic actions that will move him from one area from one labeled area in this office building to another. So different representations are appropriate for kind of different levels of abstraction in terms of the kinds of problems that we think about. So we might have been thinking about this robotic navigation problem in terms of, the level of voltage we have to send to a wheel motor to get the robot to turn a certain angle, thinking about colliding with pedestrians. But right now we're thinking at a higher level of abstraction, right? We're assuming that all of those problems have been solved somehow, and we're just interested in the problem of navigating through this environment by moving from one area to another. So that's the kind of problem that's appropriate to this representation that we're talking about today. So other kinds of problems that wouldn't be appropriate, right, that don't have these properties, so poker might be a nice example, right? Poker suffers from a lack of observability, so you don't know what your opponent's cards are. And the effects of your actions are not deterministic, right? So when you ask for some more cards, for example, there's a random element involved in which cards you end up with. So these are the properties of the problems that we're going to be dealing with. Here's how we can formulate one of those problems. So we'll call these things state space problems, and each of these bullet points is part of that formulation. So we'll have some set of states. Some subset of those will be designated as start states, maybe just one start state. We'll have a set of actions that are available to the agent in each state. An action function that maps from state action pairs. So if I take this action in this state to next states, so where will you end up? What next state will you end up in? And some function that determines whether a particular state is a goal or not. And we'll talk about this a little bit more, but the idea is we're also interested in not just finding a path to the goal, but generally we want to find the best path to the goal, and there will be costs associated with different actions. And if that's the case, we'll want to take the set of actions that gets us to the goal with the minimum cost. Okay, so looking at this, right, we could express all of this a little bit more formally in terms of set notation and function notation. But the formal representation that we're going to be more interested in today is in representing a problem as a graph, right? So much of this section should be review to you. This is the kind of material that's covered in the discrete math course or in the data structures course, right? Graph representation, so the terminology in the textbook is that we have a collection of nodes. These might also be called vertices, and a set of arcs. These might also be called edges. And when we use these things to represent our search problems, we're going to be, right, each state is going to correspond to a node in the graph, and there will be an arc between two states if there's an action that deterministically moves us from the first state to the second state. So that's how we're going to represent or think about these problems. Here's an example of representing a problem as a graph. This is that same office environment we saw before, but now it's represented as a graph. And if you look carefully, you'll see that not all of the states that were showing up in the previous figure are here, just the ones in bold, just to give us a simpler graph. So, right, this is a graph. Maybe this is our start state. Maybe this is our goal state. And the problem is going to be finding a set of edges, right, finding a path that leads us from that start state to the goal state. And you can see here that a lot of these edges are numbered, right? So those are representing the costs of taking those actions. So these probably represent something like the length of the hallway between these two rooms. So if we look back at the figure, it's probably the case that there's a long hallway between O109 and O119. And in that case, finding the minimum cost path is going to correspond to finding the fastest route between two nodes in this graph. So that's one example. Let's go to the board and do a couple more. So in the problem we just looked at in the book, there was a one-to-one correspondence between physical locations in the environment and states in the problem. But that isn't always the case. Our state can represent more complicated abstract information. So to see that, let's think of a much simpler office environment. We'll say here we only have 3 rooms. We'll label them A, B, and C. And the robot can move between adjacent rooms. Maybe he's starting in room A and his goal is to deliver something to room C. So we can get the graph representation of this problem, something like this. A, B, C. And we've got edges representing the fact that he can move back and forth between these rooms. We could label these edges, right? This is a right, this is a left, and a left. And maybe we could represent the fact that this is a start state like this, and that this is a goal state like this. So here's our graphical representation of that problem. It's a ridiculously simple problem. But let's make it a little bit more complicated. So let's assume for a second that the robot, before he can deliver what he wants to deliver, he needs to pick it up first. And in this case, we'll say that it's a letter in room B. So there's our letter. So now the agent's goal is to pick up the letter and deliver it to room C. So this description of the state doesn't capture the fact, doesn't capture any information about whether or not the robot has the letter. So what we need is a new state representation. And a natural way of representing the state now might be as a tuple. So the robot is in room A, and he doesn't have the letter. So it's a pair, right, where the first part of the pair is the location, and the second part is represents whether or not the robot has picked up the letter. So we have all of the states that we had before without the letter. And all of the states that we had before with the letter. And we'll draw circles around all of these. They look like nodes. So in terms of state transitions, we have the same state transitions that we had before. It's still possible for the robot to move back and forth between adjacent rooms. And it's also possible for him, as long as he's in room B, to pick up that letter. And for the sake of simplicity, we'll just assume that once the letter is picked up, it can't be put back down. So what that means is that we have an edge here. So this means that when in room B, the agent actually has 3 actions available to him. He can move to room A, he can move to room C, or he can stay where he is and pick up that letter. So this is now a complete graph that represents our new, slightly more complicated version of the problem. And in this case, right, our start state is here. The robot begins in room A without the letter. And the goal is here. He wants to end up in room C with the letter. And there are lots of possible paths through this graph that would allow him to meet that goal. And one of the things that we'll want to talk about next time is how to find the best path. So notice here that we added exactly one bit of information, whether or not the robot has the letter, and it doubled the size of the state space. So that turns out to be a pretty general. So every time you add a little bit of information, your state space gets a lot bigger. So one of the reasons that these problems are hard is that for any sort of non-trivial problem, the state space tends to get really, really big. And in fact, there's no reason that we can't have an infinite state space. It's very easy to have an infinite state space. We can't draw it on the board, but that doesn't mean that such a graph can't exist. So in this case, we might end up with an infinite state space if, for example, instead of picking up this single letter, this is a robot that picks up quarters, and there are an infinite number of quarters available to him, and he has infinite quarter carrying capacity. So in that case, right, the state of the robot might be represented by the room that he's in, followed by the number of quarters that he has. And there are quarters everywhere, so he always has the opportunity to pick up a quarter. It's not the most natural problem in the world, but it'll do for now. So if he picks up a quarter, that moves him to that state. If he picks up another quarter, that moves him to that state, etc. So in this case, we end up with an infinite state space. So maybe his goal is to pick up at least 5 quarters and end up in room C. So there would be no reason for him to pick up more than 5 quarters, but there's nothing in the description of the problem that stops him from doing that. That's just not going to turn out to be the optimal solution. So it's an infinite state space, even though the size of the answer is finite. Okay, so again, we now know how to encode these problems. We have no idea how to solve them. That's where we're going next.